Now, in this module, we shall learn about the importance of the refractive index measurement, which is again one of the most important properties of the glass. Now, what are the prerequisites for refractive index measurement, and a brief description of the methods used for determining the refractive index, and this is followed by a detailed description of the methods and the instruments that are used in the refractive index measurement. Let us introduce ourselves to this particular module. Now, it is actually a forensic scientist's main duty to analyze the glass fragments so as to clearly and unambiguously determine what is the origin of the sample or what is the source of the glass fragment. By and large, forensic scientists, as we have seen, are most of the time interested only in the freshly broken pieces, as they have got very sharp and clean edges. Now, these freshly broken pieces which are considered are recovered from maybe hair combings or the surface of the garments, that is, the glass which could have been broken and or acquired recently. Now, these will be compared and contrasted with the reference sample of the so-called broken glass. For example, from the scene, by way of refractive index measurements, that is a measure of the degree to which the glass bends the light, and chemical analysis tests. Now, refractive index is actually a very accurate test which can determine or which can distinguish between a large number of different samples of glasses. Now, if the recovered fragments, they vary in refractive index, if you compare it with the reference glass sample, then obviously they could not have originated from the same piece of glass. Now, chemical analysis provides a detailed information about the chemical constituents of the glass, that is, whether the glass is made from sand or any other material. Now, chemical analysis using, for example, a scanning electron microscope can be actually useful in distinguishing between different glass samples which have, although the same refractive index, but different chemical composition. Now, in addition, the surfaces of the glass fragments will be microscopically examined for the evidence of the method of manufacture and the type of object from which they come. For example, flat glass or patterned glass, both from the window panes itself, or curved glass, which may be a drinking glass, or which may be a can, or which may be a container, or which may be a bottle. Further tests may be performed to see if the source was of toughened glass, that is, forming small cubes when broken and typically found in some car windows and in door and window glazing. Now, every material we know has its own refractive index. Now, the refractive index measurement can actually give an indication of the composition and thermal history of the glass, just like the density measurement. As a result, again one can actually come to know the make of the glass. As we know that the light, it bends from its original path on passing from one medium to another, that is, light shows the property of refraction. Now, this principle of refraction is thus the basis of the different methods of refractive index determination of the glass. Refraction is much more evident in solids rather than in liquids or gases. That is why refractive index measurement actually holds importance in forensics. Glass is actually indeed an excellent medium for showing refraction. Refractive index measurement is affected by the types of glass, actually depending on its color, the manufacture of the glass and the thickness of the glass. As it is difficult to measure refractive index by direct methods, some indirect methods like immersion methods, dispersion, etc. have been used.
Definition and use of refractive index measurements. Refractive index is a dimensionless quantity which is characteristic of an optical medium and is defined as the ratio of the velocity of light in vacuum to the velocity of light in the medium, that is, N is equal to C by V, where N is the refractive index of the medium, C is the velocity of light in vacuum, and V is the velocity of light in the medium. It determines how much light is bent towards normal or away from normal. Normal is the line perpendicular to the interface of the two mediums, or in other words, how much light is refracted when the beam enters a material. This is also described by Snell's law given by N1 sine theta 1 is equal to N2 sine theta 2. Theta 1 and theta 2 are respectively the angle of incidence and the angle of refraction crossing the interface between the two mediums with refractive indices n1 and n2. The velocity decreases when a beam of light is traveling from gas to solid. In other words, the light bends downwards. This allows the determination of the refractive index of glass, that is, how much light is refracted on entering the glass. Since refraction is much more evident in solids than in gases or liquids, thus glass is indeed an excellent medium for showing refractions. Refractive index is always greater than 1, since the light travels fastest in vacuum. For glass, the range is between 1.4 to 1.7. Refractive index measurement is affected by types of glass according to its color, manufacturer, and thickness. The refractive index of several glasses is given below. Headlight glass 1.47 to 1.49. Television glass 1.49 to 1.51. Window glass 1.51 to 1.52. Bottle glass 1.52 to 1.52. Ophthalmic lens 1.52 to 1.53. Common flat glass 1.51 to 1.53. Temperature T and wavelength lambda of light influence the refractive index of glass. Temperature affects density. Density further affects velocity of light beam as it passes through the sample. N is directly proportional to 1 by T and N is directly proportional to 1 by lambda. Thus, refractive index thus gives an indication of the composition and the thermal history of glass. By thermal history, we mean the last set of conditions under which a glass has been cooled from its softened state. Refractive index is the most commonly measured property as precise refractive indices can be measured rapidly on the small fragments found in a casework, aids in the characterization of glass, provides good discrimination potential. It is possible to determine the refractive index of very small glass fragments also, which can be found on the crime scene. Prerequisite for refractive index measurements. Material recovered should be examined to determine if it is glass and then prepare for another analysis. Glass fragments may be crushed to produce sharp edges. There are various methods of crushing glass. Large fragments may be crushed using a mortar and pestle or a glass crusher. Small fragments may be placed on a slide in a small drop of immersion liquid and crushed in situ using the tip of a tungsten probe. Slides and cover strips should be cleaned prior to use with the help of solvents such as acetone, ethanol, or methanol and a lint-free wipe, thus making sure that the solvent has evaporated before mounting the samples. Since refractive index is a function of temperature, it is necessary to note down the temperature also. Different instruments used for refractive index measurements. There are a number of instruments to calculate the refractive index of glass fragments. Some of them are as follows. Glass Refractive Index Machine GRIM. Glass Refractive Index Machine designed by Foster and Freeman utilizes the oil immersion, temperature, variation method for the determination of the refractive index of glass. GRIM offers a simple tool to improve focusing and provide a highly accurate temperature control with very little drift for optimal reproducibility. All images of the glass fragments can be saved along with the particular measurements and graphs for later appraisal. Besides a high-spec computer system, GRIM comes with a phase contrast microscope, hot stage, GRIM main processor unit, and the GRIM software package. A sophisticated package of statistics function, correlation graphics, and export function to MS Office software built up to a versatile forensic tool for glass analysis. Refractometer. It is a laboratory or field device for the measurement of refractive index using Snell's law. Many type of refractometer is Abbe refractometer. The only thing is that the methods involved in Abbe refractometer requires pieces large enough to polish. It has got built-in thermometers and requires circulating water to cool the instrument and fluid temperature. In principle, it measures the angle of incidence required to just begin the total internal reflection for light propagating from a standard glass hemisphere of high index to a sample of lower index. In practice, due to easier alignment of the beams, the light is incident in the reverse direction into the interface between the sample and the glass hemisphere. Accurate measurement of refractive index using this instrument, however, requires a good contact between the sample surface and the top surface of the prism of the instrument. Dispersion can also be measured by Abbe refractometer. Hot stage microscope. Hot stage polarizing microscope is used to study the optoelectronic and thermal behavior of the liquid crystal, organic, and polymeric samples. In heating stage, samples are positioned between commercial slide and a cover glass. The photo monitor allows determination and plotting of the light intensity of the field of view as a function of temperature. Thus, material phase transitions information qualitatively as well as quantitatively can be determined. It has a furnace with a heating element beneath and above the sample, which guarantees outstanding temperature uniformity in the sample. In the method using hot stage microscope, the glass sample is immersed in the high boiling liquid. Hot stage polarizing microscope is an important instrument for the characterization of organic liquid crystal polymers, organic polymeric materials, glass, and nanocrystalline materials. Qualitative and quantitative information on the chemical or physical changes occurring in the sample. Example: color changes, melting, polymorphism, crystal transformation, or decompositions can be detected. Phase contrast microscope. Phase contrast microscope is an interference microscope which converts phase shifts in light passing through a transparent specimen to brightness changes in the image. Phase shifts themselves are are invisible but become visible when shown as brightness with variation. Polarized light microscope. Polarized light microscope is a microscope equipped with two polarizing elements. One of them is the polarizer, which is located between the light source and the sample, while the other is analyzer, which is located between the sample and the observer. Different methods for calculating refractive index. It is not possible to measure refractive index directly, as it is not possible to practically measure the speed of light as it passes through the glass. Instead, indirect methods are used. We can detect transparent objects in air, such as glass fragments, as they refract light. Suppose two objects have got same refractive index, then it would be difficult to observe any difference in the light that has passed through them. If a piece of glass is immersed in a liquid whose refractive index matches that of a glass, then the glass becomes invisible, as The light that passes through the glass would be same refractive index. The various methods are based on this principle only. Some of the methods are as follows in brief. Emmons double variation method. In this method, glass is immersed in oil. Here, a circular water bath is used to heat the oil with glass fragment immersed in it. In a way, this is a temperature variation method. Backline method. This is a method to determine refractive index of a transparent particle relative to its surrounding medium. Its advantage is that not only indicate the difference between the refractive index and the liquid, but it also indicates which possesses the higher value. Here, the index of refraction is compared to that of an immersion liquid using a microscope. The sample is placed in the immersion liquid of known refractive index. The sample must be illuminated by a beam of rays converging at an extremely acute angle. This can be achieved either by reducing the aperture of the condenser on the microscope or by raising the condenser. As the microscope stage is moved away from focus, there will be a bright line contouring the perimeter of the glass specimen. This is the backline. If the refractive index of the immersion liquid is lower than that of the glass, the backline will move inside the object when the distance between the objective lens and the specimen is increased. Decreasing the distance will also cause the backline to move outside the specimen. If the liquid index is higher than that of the sample, the backline will move in the opposite direction. Automated glass refractive index measurement. This method is also temperature variation method, but here glass sample is not immersed in oil. Temperature has a very important influence on the refractive index measurement. Therefore, the temperature of the prism and the temperature of the sample have to be controlled with high precision. There are several subtly different designs for controlling the temperature, but there are some key factors common to all, such as high precision temperature sensors and Peltier devices to control the temperature of the sample and the prism. The temperature control accuracy of these devices should be designed so that the variation in sample temperature is small enough that it will not cause a detectable refractive index change. The refractive index is calculated automatically from the data. Dispersion staining. This technique is based on the principle of dispersion. Dispersion is the variation of refractive index with the wavelength. Longer is the wavelength, lesser is the refractive index in comparison to light of small wavelength.
Now, to summarize what we have learned in this module. Now, in this module, we have learnt the measurement of refractive index of glass, just like the density measurement or the elemental analysis actually holds importance in forensics. It gives an indication of the composition and the thermal history of the glass, just like density measurements. So, it actually again we can say becomes possible for the forensic scientist to know the make of the glass fragments, and this can serve as a major evidence to solve the criminal case under consideration. Now, it is actually the process of refraction which forms the basis of different methods used for determining the refractive index of the glass fragments. Now, there are large number of instruments which are used to calculate the refractive index of the glass fragments. Now, for example, you have glass refractive index machine, which is designed by Foster and Freeman. It utilizes the oil immersion or the temperature variation methods for the determination of the refractive index of the glass. Now, dispersion can also be measured by Abbe refractometer. It is not possible to measure refractive index directly, as it is not possible to practically measure the speed of light as it passes through the glass. Instead, indirect methods like immersion methods are used. Now, Beckline method is used to determine the refractive index of a transparent particle relative to its surrounding medium.